much, Stan. And thanks to everyone for being here. I'm going to talk about the Fluid Interface Reaction Structures and Transport Center, which is primarily located at Oak Ridge, and I'm the director. And our mission is to develop fundamental understanding and validated predictive models of the unique nanoscale interface, blah, blah, that will enable, of course, transformative advances, not incremental or improvements, but transformative advances in electrical energy storage and catalysis. So our logos kind of summarizes our program. We look at interfacial structure and dynamics, transport reactivity, and our ultimate goal is model-driven synthesis of novel interfaces. So we're looking at the interface kind of from the fluid side. A lot of the talks and presentations that we've heard so far, I think, have been looking at the interface from the solid side up and really considering the details of the materials, the substrates. We're very much looking down through the fluid towards the surface. This is from our most recent all-hands meeting. The centers consists of people at Oak Ridge, Argonne, and 7 partner universities, Delaware, Drexel, Minnesota, Penn State, Vanderbilt, and 2 of the California campuses, and 2 of our notable participants are in this room. Paul Fenter directs the CEAS Energy Center, and Dan Scherson is on our advisory, but I think he's on the advisory board of every energy center. I'm not sure, but he's also the president of the Electrochemical Society, so it's very nice. And at the all-hands meeting, he worked hard to keep us honest. Although, you have to BS a little bit in order to get through with science. Okay, so I don't understand the organization of the symposium, but all of the talks from the first center have already been presented. Majid's this morning. And some very excellent talks. And these are the people that really know the science. So if you have any substantive questions, you really should ask them. And there's a number of other firsters at this meeting who are giving talks or have given talks in various symposia throughout the meeting. And I hope I didn't miss anybody. I think I caught everyone. It's a great bunch of people and a real pleasure working with them. So here's how we're organized. We have 2 thrusts. We had 3 thrusts, but we're sort of minimalizing. We're down to 2 thrusts. And this is interesting because somebody mentioned previously that they had a theory thrust. I think it was you, Stan. Yeah. Had a theory thrust, but decided that didn't work. And so they distributed their theorists out into the grass. And we've kind of just done the opposite. And the reason for that is because this barrier is already semi-permeable or really very permeable. And so we are interacting a lot together. But it just makes it more efficient for us to budget our computational resources and make sure that they're focused on supporting the experimental work. And so we're experimenting with that in our second round. We'll see how it works. What we feel is that a modeled interface is inherently a simple interface. Simple in the sense that you know exactly what you're modeling, and so you know exactly what this in silico interface looks like. And then we try to do experiments that validate or guide those models, and that's a very difficult task, as many of you know. Producing a real interface that is as clear and simple and perfect as a model interface is a grand challenge. And then in thrust 2, we look at real interfaces. We synthesize them, we characterize them, we probe them, and try to develop fundamental understanding of how to make better interfaces using the input from thrust 1. So our cross-cutting themes are interfacial transport, which really has to do with the interfacial structure and transport properties really dominate energy and power density in electrical storage devices. And interfacial reactivity. So that reactivity and the dynamics, the motions of molecules and their absorption and desorption and so on, really control electrocatalysis and pseudocapacitance. We've been very productive, and I put this slide up here maybe as a plug for J. Caesar and other new energy centers that we've really hit our stride just in the last 2 years. So we're at our maximum productivity now, so that's DOE should take heart and fund these big projects for at least 10 years, maybe 15. So I don't know where we'll go. This is not an exponential curve, but it's still rising. And we've published just in the last 2 years a number of papers in terms of H-index, the top journals in our field. Okay, so this is a theme that's been throughout this conference. Is capacitive storage or ion adsorption, non-redox electrical double layer formation being the primary feature of supercapacitors, and intercalation or surface or bulk redox reactions being the heart of battery research. And this nice science paper by Yuri Gagazi and his colleagues just last year kind of set the stage for defining how you tell the difference between a battery and a supercapacitor when you shrink things down to the nanoscale. So in order to increase energy density and power density in capacitors, we want to always push higher surface area, higher, smaller pores. And in order to increase the power density of batteries, we also, as Esther talked about this morning very nicely, shrink the particles, the active species, down to very small dimensions. And so this is Q over Q max. So even though this looks like a capacitor, it's really pouring out power. And so the overall response starts to look a lot like a capacitor in the sense that you're no longer severely limited by bulk diffusion. And so to achieve this goal of increasing both power and energy density, we really need to consider both kinds of processes, and that's what we're doing in the center, primarily from the perspective of capacitor and supercapacitor behavior. We are in a very fortunate position at Oak Ridge. This is where I live, and this is where two of the world's fastest open source computing platforms are available. Right up the hill is the spallation neutron source, and over the next valley is the high flux isotope reactors, two of the world's most intense neutron sources. And we collaborate with Paul Fenter's folks at Argonne using the advanced photon source. So what I would emphasize is all of these facilities, as well as the Center for Nanophase Material Science and nanoscience centers at a number of the other national laboratories, are user facilities that are available free of charge from DOE. So certainly everyone should put that into their operational models and consider the advantages of writing two-page user proposals to these facilities and gaining access to world-class capabilities. So what do we look at? We look at aqueous solutions, polar organic solvents, not so much, and room temperature ionic liquids. You've heard a number of talks about these already, so I don't need to go into the details, but very simply, water is safe, cheap, good solvent, low viscosity, but it has this severe voltage stability window as an electrolyte. Organic solvents expand that voltage window with a lot of the good characteristics, but they're flammable and they're volatile. Ionic liquids are expensive, but they have these really nice temperature stability range. They have very low vapor pressures, almost no vapor pressure in many cases. And they have this potentially very large voltage stability window, which Majid mentioned very nicely this morning. So, the other advantage of ionic liquids is they're synthetic. They can be tailored into an amazing array of sizes, shapes, charge densities, which really makes it nice to understand fundamental processes. Okay, so we also, in capacitive world, carbon is the king. So it is cheap, earth-abundant, light, chemically inert, and can be synthesized into a truly amazing array of sizes, shapes, surface functionalities, so on. So this is just 3 examples of graphenic materials with planar structure. Majid talked about carbide-derived carbons with very high porosity and very small pore sizes, very tight ranges of pore size distribution. Sol-gel synthesized ordered and disordered mesoporous carbons with larger pore sizes but very uniform pore sizes, and these materials that don't exhibit internal porosity but external high surface area, so exohedral interfaces, these carbon onions and materials like that. And we've published, I just note that, I don't know if Sheng's in the audience here, but this paper has already gotten over 600 citations, so doing very well. So this is an example of a simple interface. This is X-ray reflectivity work. This is a logarithmic scale of reflected X-ray intensity from graphene formed by thermal annealing on a silicon carbide single crystal substrate in contact with water. These are the Bragg reflections. So we're looking at the energy between Bragg reflections, and the shape of this intra-Bragg crystal truncation rod is very sensitive to the surface structure. The guys also did contact wetting angle measurements of what does water look, how does water see a single graphene layer on the surface versus multiple graphene layers. And what's clear is that this first layer of graphene is very different from bulk graphite or multi-layer graphene in the sense that it's much more hydrophilic and also exhibits different concentration. So this is something that is kind of universal to liquids at solid surfaces. They're liquids because the molecules like each other and they interact with each other to form a three-dimensional, although fluid network. When they meet a surface, they not only no longer have their buddies around them, but their dimensions are of the size of the atomic arrays in the substrate. And so they interact very strongly with that substrate always. There's always layering. So this is a plot, so that's the surface, and these are dense layers of water molecules moving away from the surface, even in water extending up to maybe 10 angstroms away from the 10 water diameters away from the surface. In order to understand these X-ray profiles, we hit this with computational modeling, all out of classical MD, as well as ab initio approaches. And the punchline is that in order to explain all of this behavior at both multi-layer graphene and monolayer graphene surfaces, we had to tweak the computational models and introduce surface defects in the form of hydroxyl defects decorating the surface. And that gave us a nice match with the X-ray reflectivity. So even this, we tried to make a perfect simple interface, graphene on planar graphene, but it's stepped and multi-layer and also defective. And so this is a pretty typical example of about as simple as you can get with an interface. So taking that to the next level, one of our recent papers looked at single-layer graphene in aqueous solution and how can we engineer or understand selective proton transport through that defective graphene. And this is kind of a poster child paper from the center. We have 5 of our Oak Ridge argon and I think not argon, right? 5 partner institutions involved in the research. 7 of our first center students and postdocs are among the lead authors. And this work combines single-layer graphene synthesis, very large graphene sheets, which could be synthesized and transferred to a substrate, high-resolution TEM studies of the defect densities and structures, second harmonic generation studies to establish the proton transport kinetics, and both reactive force field and ab initio MD simulations to elucidate the reaction mechanism. And the mechanism involves passing protons from, here's a hydronium ion in solution, passing a proton to a surface hydroxyl group. There are three hydroxyls above the defect and 3 hydroxyls below the defect. and I'll show you a movie of the growth mechanism process that was identified as the way protons shuttle among these hydroxyls and then eventually pass through the pore to the solution underneath. So, you know, this kind of harks to the work that Paul Fenter's group is doing with putting graphene on active materials, on, for instance, LMOs, and how one might get selective ion transport. This could also be the ultimate fuel cell membrane, for instance. Okay, so we've also done some work with how do surface defects such as ketone groups influence proton-coupled electron transport reactions. In this case, it's a purely theoretical study of the simultaneous shuttling of electrons and protons between an electrode surface, a graphene surface, and a ruthenium compound in solution. In this example, our X-ray reflectivity folks found that plasma etching of graphene, of that single layer graphene on silicon carbide, allowed things like phenanthrene quinone to strongly zorb on the surface and yet still undergo redox reactions. What is the payoff for that? For instance, we had done studies of the absorption of a variety of quinones on onion-like carbon surfaces, which are inherently defective, and we see very nice capacitive performance, particularly at lower scan rates, pseudocapacitive behavior. So this is the capacitive behavior of the onion-like carbon, bare onion-like carbon electrode surface, and here is the capacitance after being loaded with various quinones, and we've published a number of studies on that. And this gives this pseudocapacitive behavior is advantageous in the sense that cycle life is very good, just like a capacitor. So this is 10,000 cycles. You see very little fade in performance, and yet we're boosting up the energy storage. Okay, we've worked a lot with ionic liquids, and you've heard a lot about them. These are some of the types of ionic liquids, mostly imidazolium, so this carbon-nitrogen ring, mostly imidazoliums with various carbon side chain or alkane side chains. We've done a lot of work with TF2N, also FSI, which is just shorter smaller than this ion, but also even smaller anions like BF4 and PF6. So one of the advantages of ionic liquids is they're just like molten salts. They are molten salts, and so they have eutectic behavior. For instance, this mixture of piperidinium and pyridinium, I think I said that right, FSI ionic liquids is a eutectic mixture with a very low melting point. And so no freezing down to minus 80 centigrade. And we were able to show that an ionic liquid, a onion-like carbon electrode functions very well with these large cations, allowing capacitive performance, very nice power and energy output, even down to all the way down to minus 50 degrees centigrade and up to 80 degrees centigrade. So this is, so Siberia and the Mojave Desert, I guess, is the range that we're interested in. Majid talked about this morning, and Katie, have you already given your talk, Katie? Yeah, okay, well, if you want to know more about this, ask Katie. But the bottom line is here that real supercapacitor electrode surfaces show a range of pore sizes, and this is a film onion-like carbon electrode surface showing the distribution of pore diameter. So, you say the pore, really small pores, bigger pores here, and big pores there. How does that interact with a mixed electrolyte? And as Majid talked about this morning, the pure CmimTFSI, C2MimTFSI, shows this asymmetrical behavior of the two electrodes during charge-discharge cycles. Also, a pure C2MimBF4, much smaller anion, shows this asymmetrical behavior, but a mixture of the two, a magic mixture 80-20, gives a perfectly symmetrical behavior. And the advantage there is that neither electrode experiences an extreme potential. And the net result is that there is a much improved cycle life of this electrolyte, even at 3.5 volt cycling window, compared to, for instance, the pure EM-TFSI, which degrades after about 5,000 cycles. This was work that Ahmed talked about yesterday, looking at the structure of ionic liquids at this graphene on silicon carbide using X-ray reflectivity. This is just an example of the density profiles away from the graphene surface at +1 volt and -0.4 volts. This is the purple is the total computed electron density. In other words, the density of all electrons around every ion at the interface. This is the surface. So this is the first layer absorbed ions. In the case of negatively charged surface, we have cations concentrated at the surface, and at the positively charged surface, we have negative anions concentrated at the surface. But the MD simulations give us the ability to predict the distributions of the individual ions at the interface. We get a pretty good match on the total electron density calculated from MD. Some discrepancies out a few layers away from the surface, but the major interactions are captured. And as Ahmed discussed, and I won't go into any detail, in voltammetric cycling between these two extremes, we find a fast response and a much slower response, up to 10 or 11 seconds, characteristic response time, which shows hysteretic behavior. And the current interpretation, which we're getting from combined X-ray reflectivity and CMD modeling, is that the surface consists of a patchwork of cation and anion terminated structures or local pancake structures of layered ion distributions that simply shift in their relative abundance as one cycles through potential. But as Ahmed showed, even slowing the scan rate down to very low scan rates, this hysteretic behavior of bistability persists, and this is a current topic of great interest in our center. We're also able to probe that interfacial structure using atomic force microscopy, as Jeremy talked about yesterday. Pushing a probe tip towards the surface and measuring the force on the probe tip as it pushes through ion layers approaching the surface. So here's the open circuit or the 0 point of charge structure of this EBM-TFSI at the interface of graphene. This is a HOPG graphite in this case, so very, very bulk graphite behavior. And still we see this nice layering, which is detected by force microscopy. And that changes as you go from positively charged to negatively charged interface. And we can also computationally model that. This is MD simulations at this open circuit potential, where you see that it's really the anion layers that are giving rise to this signal, which is something that we don't really quite understand yet, but apparently the anion layers are stiffer than the cation layers for this particular electrolyte. So that's something of great current interest. This is some brand new work that Jennifer is going to talk about tomorrow afternoon at 5 o'clock. So I hope people will stay around and go to her meeting. But she's detecting, so this is the surface topography of the HOPG she's studying. And then we're looking from that surface down into so this is going down into the ionic liquid. So this is upside down from this one. I should have turned them around. But what she's detecting is topological defects. So here you see one of these that looks a lot like a discontinuity in a crystal structure. And these persist for long periods of time. So this is a topic, again, of great interest to us, which we are trying to understand, trying to improve our understanding, and how does this affect capacitive behavior. We've looked at surface curvature effects. How am I doing on time, Stan? 5 minutes. Oh, God. Oh, geez. Okay. We've looked at surface curvature effects computationally. So ionic liquids are big, and they actually, because of pi-pi stacking interactions with graphene there, they overcompensate surface charge. Quite often the cations are strongly absorbed. And so on a flat surface, you get packing problems. You get excluded volume problems that limit the capacitance as a function of surface potential. So you get this camel-shaped capacitance curve as a function of surface potential. But as you make that surface curved and shrink the radius of curvature, you get higher and flatter capacitance behavior from the same material in a sense. So this is surface normalized. And so we can get capacitance over a much wider potential window than we can achieve with a flat surface. So this concept was taken, or actually the experiments preceded the modeling, to the fabrication of a micro-supercapacitor electrode array consisting of these onion-like carbon particles in an aqueous. This is an aqueous electrolyte showing extremely high rate handling capability for this open architecture, this exahedral architecture. Here's a Ragone plot of some typical micro. Here's a lithium thin film battery, very high energy density, but not very high power density. But electrodes like this, fabricated from activated carbon and carbon onions, give both high energy and power density, with the carbon onions giving even higher power density. So in other words, that open architecture and those curved surfaces really enhance the power output as well as boosting up the energy output. We've done a lot of computational modeling of slit pores and how electrolytes and ions enter and leave those pores. I won't go into the details, but ionic liquid, like simulated liquids, tend to form first this anomalous capacitance at about 1 pore diameter, so a slit width about the size of the ions gives an anomalously high capacitance. Then there's a trough, another capacitance peak, and this is indicative of the layering of the electrolytes within the pore. Whereas the same ions dissolved in a simulated dielectric medium give this first capacitance max, but then decay to kind of a uniform capacitance, which is actually higher for the same ion diameter behavior. And that is because the dipoles of the solvent are actually contributing to the overall capacitance. So orientation of these surface dipoles is contributing to the capacitive energy storage. We were able to reproduce the first two of these for an ionic liquid, CmimTFS2, TF2N, in carbide-derived carbon with very careful control of pore size. So this is 1 pore diameter, 2 pore diameter. So the first two bumps were reproduced computationally, and the first one has been reproduced experimentally. So taking this coarser grain CDFT model, we can play all kinds of games like varying the dielectric constant of the solvent. And what we see is that as we take a dilute spherical ions in a strongly dielectric medium, it gives this uniform capacitance at large pore size. But as you shrink that dielectric property, this ionic liquid-like behavior reemerges even for a dilute electrolyte. And it also gives us the ability to predict what's the maximum dielectric properties that will give you the maximum capacitance. So in this case, it just happens to coincide with something like acetonitrile. And what's going on, what's giving rise to this is simply, Esther asked this question yesterday, at 3 ion diameters, you can fit 3 ions into the pores, and at less than 3 ion diameters, you get interference. And so this is an additive property of the double layers at the 2 interfaces for sort of interacting in a wave-like interference behavior. With neutrons, we can look directly into pores. So this is a ordered mesoporous carbon. There's a strong neutron scattering contrast between the carbon septa and the holes, which gives rise to this black curve. So that bump it corresponds to the pore distribution of the empty pores, and then we can selectively fill those pores with an ionic liquid and see the drop in scattering intensity, and we can use that to extract the density of that fluid in the pores. And we did a very elaborate study, which I won't go into the details, but here is the, so what we surmised from our studies was that these mesoporous carbons, the cylindrical pores, are decorated with slit-like pores along their walls, and we were able to do MD simulations of the behavior of this ionic liquid, it's CmimTIF2S, in the slit pore configuration, gives very high density, and also as submonolayer, several monolayer and full pore filling, and extract the density of the fluid, the bulk density, average density of the fluid in those pores, which shows a very good match between small angle X-ray and neutron scattering with the predicted behavior, predicting up to three times the bulk liquid density in these slit-like pores. We also did neutron spin echo experiments to probe the diffusional dynamics of those liquids in these various configurations. Again, we get a very good match between modeled and measured dynamics, and I won't go into the details of that, but the bottom line is that we see slightly faster diffusive motion in this configuration than for the same ions decorating just the surface layer of the cylindrical pores. And the origin of that is really disruption of the cation-anion correlation in these slit pore environments. Jeremy talked about electrochemical strain microscopy. This was patented by CNMS and the first center, licensed to Asylum Research, and is now available through user proposals to our CNMS. And we're probing not only ion intercalation in redox active materials, but also the effect of charge and discharge of nanoporous supercapacitors on, in terms of volume effects. And again, I don't have time to go into the details of this, but we're predicting the pressure exerted by the electrolyte on the pore walls as a function of charge state. And we can measure that by electrochemical strain microscopy by the expansion and contraction of the nanoporous electrode in contact with the electrolyte and get a very nice agreement. But we can also vary that strain measurement as a function of voltage sweep rate, and this deviation gives an indication of the transport dynamics, the rate of, the ability of the electrolyte to go into or come out of the interface. We have also developed a flow TEM cell with electrochemical capabilities. I won't talk about that at all except to show this, well, maybe I'll show this neat little movie. Yeah, here we go. This is oops. Well, okay, I won't show it. So it's SEI formation at a gold electrode surface. Well, sorry, that movie doesn't work. Forget that. The very last thing I'll talk about, or the last two things I'll talk about, we got a minute or two? 1 to 2 minutes, okay, that's enough. Michael Naguib is here at this conference. Also, he did his PhD work at Drexel developing these new two-dimensional materials that are kind of like graphene, kind of like clay minerals, but they are transition metal carbides and nitrides, so early transition metal, carbon and nitrogen, and there are many solid solutions in here. You produce them by stripping the A out of a max phase. It's a layered three-dimensional structure to produce these nice flaky layers that look a lot like graphene, and in fact have can be semiconducting, can be conducting, or can be insulating. But instead of carbon terminations, they have transition metal terminations, which can be, which make them hydrophilic and ionophilic, having many interesting new capabilities. Jeremy talked yesterday about making some strain measurements of during charge and discharge of a paper-like Maxine electrode, where instead of ion intercalation causing expansion, in this electrical double layer insertion, the ions actually cause contraction. Now, the potassium is big enough to not cause much contraction of of this interface during charging, but lithium really changes the volume by 15%. It's really a large effect. So this is a brand new material that we're very excited about. It can be fabricated into all kinds of materials with very high capacitive behavior. So I encourage you to go to our website if you want to learn, or talk to Michael if you want to learn more about that. I'll skip this one. There's just a little too much detail there. And I'll close by talking about the work that Majid mentioned this morning, getting away from the energy density problem with capacitors by a flow configuration that allows you to scale the total energy density by just simply scaling these flow reservoirs. The trick here is making a carbon slurry that flows enough to go through these tiny electrodes and efficiently not only transfer electrons by collision with the surface and then with other carbon particles to transfer that electrical charge and so that surface charge throughout the bulk solution, but also to not have a lot of pumping penalties. We're doing a variety of studies to understand how do these slurries store charge, how do you control their flowability, can you decorate them with redox active surface components, and what is the charge transfer and ion absorption mechanism in this kind of environment. And Kelsey Hatzel, I don't know if Kelsey's already given her talk, but she will be talking about this more in detail. She made this nice movie of a flow cell. This concept can be adapted to normal ion insertion by having graphitic material that can undergo ion insertion reactions as one of the flow fluids, or both of them. And this concept can be adapted to do all kinds of things like capacitive storage, flow battery configurations, and water treatment and water desalination. And with that, I'll close, and thank you very much. You know, that's a good question, and I don't know the answer. But it's deployment of these kinds of capabilities is purely an economic issue, right? Safety, economics. Fundamental understanding is what we do. Trying to fundamentally understand the processes to the point where you can manipulate the electrolytes and the substrates to achieve better performance, transformative performance, right? Making something commercial is a whole different ballgame, and it's subtle and it's confusing, and I'm not in that game. So that's, you know, I guess I just won't answer that question. But I think, you know, making things cheap, high power density, high energy density, and safe is the key.
I think of my question, well, perhaps I didn't phrase it right, but I'm not so much concerned in the economics, but in the actual performance. Forget about making stuff.
Right.
Okay. So where is the scientific challenge in order to improve the performance, even though the device may be too expensive to be sold there?
That's a good question. So I think that, you know, everybody has talked about that, you know, the Gouy-Chapman-Stern model of electrical double layer no longer applies. But then the people, you know, I got it started in this from the geochemistry game, and you have specific ion absorption on mineral surfaces, so this overcharging is kind of normal. It's what you always get. So if all you have to do is introduce an equilibrium constant for specific absorption to explain that overcharging behavior. But the transport of ions, when you scale the system down to the dimensions of individual ions and solvent molecules, where you have excluded volume effects, where ions can't go, an ion can't go unless it pushes something out of the way, and if that something has nowhere to go but that way, then you've got a real problem. So in other words, apparently, you know, this is an observation that I didn't even talk about, but we're seeing this essentially the same capacitive behavior with nanoporous carbon particles that are 70 nanometers, even bigger, as we are with tiny little. So in other words, this charging and discharging doesn't appear to be transport limited. I don't really understand that. We don't understand that yet. Maybe these guys do, but I don't. So, you know, there's a transport aspect, but also a charge separation aspect involved in energy storage in these systems. And I think that's the frontier of, and with ionic liquids, it's what's the deal with this liquid crystal-like behavior at interfaces, limiting our understanding. Okay.
We've met this stop there. Thank you.
Thank you very much.